Good morning, this is Deep Generative Models. Today we are going to talk about the architecture of Stable Diffusion and discuss some methods for fine-tuning or retraining diffusion models. We'll start with some basic topics, since Stable Diffusion comes in various different variations and versions. For example, the latest one is the Stable Diffusion 3. Which is very different than the previous architectures. There are also various new techniques for fine-tuning that is developed in last years. We'll cover some more fundamental and classic methods compared to the latest ones. Our primary focus today will be on explaining the structure of latent diffusion, as well as methods like classifiers, guidance, classifier-free guidance, texture inversion, dream boost, LoRa, and ControlNet. As usual, you can find the lecture materials on our lecture website. So this one, the Stable Diffusion and the fine-tuning are corresponded to today's materials. Let's start with the architecture of Stable Diffusion. Stable Diffusion is a deep learning text-to-image model released in 2022 that leverages the diffusion techniques. In general, diffusion models usually trouble with very high resolutions like 500 by 500 or above. Stable Diffusion uses a technique called the latent diffusion to solve these issues by doing the diffusion process on latent space instead on the pixel space. It is currently the most popular model that has a weight publicly available. It can generate very high quality images. It's regarded as part of the ongoing artificial intelligence boom. The image on the right-hand side is generated by Stable Diffusion using the text prompt, a photograph of an astronaut riding a horse. This prompt became quite popular as a creative example of text-to-image generation, demonstrating the model's ability to invent new things and understand the meaning of the given prompt. It is not only something that doesn't occur in reality. Back then, it is also very hard to find a similar image online. So it can be as a proof that the model can actually generate novel images, not only just copy images available online. So the primary purpose of the Stable Diffusion model is to generate highly detailed images based on text prompt. However, it also has many different applications, such as inpainting, that is filling the missing part or corrupt parts in an image, or outpainting, that is extending the image beyond its boundary. In previous lectures, we demonstrate how Stable Diffusion can be used by running Comfy UI. The first version of Stable Diffusion 1.1. The first version of Stable Diffusion is 1.1. There is no 1.0 version. And very soon, within 2 months, it comes 1.2, 1.3, and 1.4. Each new version provides a higher quality of the generated images. Its rise to popularity was just as rapid, gaining recognition even outside the academic circles and among the general public, followed by 1.5. which is significantly improved quality. 1.5 is trained with initialized weight of version 1.2, not 1.4, and it is released by Runway ML. Previous versions are released by Comfys, a group called Comfys. Later comes the version 2.0, 2.1. These versions are retrained with filter dataset, which is supposed to be more clean. Whether the quality of the generated image is better than 1.5 is arguable, depends on the content type that you wish to generate. And later they come Stable Diffusion XL, which is focused on training on high-resolution images. The size of the model is 3.5 times larger than previous versions. And there is also an XL Turbo, which is distilled from XL 1.0 to skip a few inference speed steps, so it can run much faster. And the latest one is Stable Diffusion 3.0. The architecture of 3.0 is totally different than the previous models. It is actually a family of models because it contains models with different sizes, start from 800 million parameters to 8 billion parameters. The pre-trained weight is not released unlike the previous versions, but the API is available to the public. Today we are focused on introducing the original architecture. Following the timeline, let's first discuss VQGAN. While it's not a diffusion model, it is also a text-to-image model. By the name, you can see that it incorporates with the VQ component from VQVAE and pairs it with GAN. In addition, it also uses transformer in between to integrate text prompt so that you can generate the image corresponding to a text prompt. So the VQ part is come from VQVAE. It uses the VQVAE approach where the image is encoded into a lower dimensional representation. The encoded representation is then quantized. You can see right here, it is quantized into a quantized representation. Then it uses a decoder to decode the quantized latent to reconstruct the image. So you may see that it is the same as what the VQVAE is. The difference is the training procedure. The training procedure incorporates with the GAN training procedure, so it has a discriminator. So that's the first differences. The second difference is that instead of using pixel CNN or pixel RNN like VQVAE, it uses a transformer to generate the discrete latent, the quantized latent, when we want to generate the image. So because the quantized latent is indeed just can be considered a sequence of tokens, so it works perfectly with a transformer that handles the language models. So to generate quantized latent with a text prompt, we simply encode the text into token, into its embeddings as a prefix. Then we train the transformer to generate the corresponding latent. So when training, you need to have a dataset with image and a text pair. So what's the connection between VQGAN and Stable Diffusion? There are many. The first one is this architecture. This model is also developed by CompFIS, the group that initially proposed the Stable Diffusion. And secondly, like this model, Stable Diffusion is also work in latent space. So by saying that work in latent space, we mean that we first has an encoder to encode the image into a latent, which is usually in a lower dimensional representation. And when we do something in this latent space, then decode it back to the pixel space. So Stable Diffusion, like VQGAN, it is primarily working in the latent space with the help of a encoder and a decoder. And the last one is many culture or many conventions come from the time with VQ gain. Back then, it already has a lot of people using VQ gain to generate art or trying to experiment with prompt and generate interesting images, just like what we do for diffusion models today. Except the population of people doing so is much smaller. But a lot of things are in common, like what we call the prompt engineering or prompt trick today. They also have something like that back then. One trick that I remember, and it is a famous trick, is called the Unreal Engine trick. People are trying to generate something has higher qualities back then because the model is not as good as today. So one trick they found to improve the quality of generated image is by adding a phrase called the Unreal Engine into your prompt. When you wish to generate some image, you can simply add the Unreal Engine, this phrase, at the beginning or at the end or in your prompt, and the generated image will suddenly has a higher quality, higher visual qualities. People hypothesize that it is because usually a game is developed in Unreal Engine usually has a better visual quality, a better graphics quality. So the model learns the correlation between the phrase Unreal Engine and the higher quality. So that's why when you add this phrase into your prompt, usually you will generate the images that has a better visual qualities. So it's very like the prompt engineering we do for images today. Okay, so next we wish to discuss the latent diffusion models. So you can see on the screen, this is an illustration of the architecture of the latent diffusion models. Latent diffusion models is also proposed by Confis group. The same team brought us the VQ gain and stable diffusion. So earlier we mentioned that diffusion models usually struggle with training on high resolution images. So when I mean high resolution, I mean images with 500 by 500 or above resolution. So it is often challenging to train the diffusion model on high resolution images because it is a very high dimensional vector space. So it requires a lot of computational resource, which translate to we need a lot of time and the machine and the cost to train a model that converge for generating high resolution images. So a lot of people study the solution to this issue. The latent diffusion model proposes a solution to this issue. So instead of working on the pixel space, latent diffusion shifts the process into the latent space. So why does this work? Let's recall that the lecture in last week, we have introduced the principle and the theories about the diffusion models. All of the process, diffusion process, denoising, and the forward and the denoising process works on vector space. In fact, we simply treat the image as a vector. So in principle, it should work just fine on other vector space because the theory doesn't has anything specific for image or pixel or like red, blue, green color related stuff. All it works just on vector space. So in principle, theoretically, it should performing just fine on other probabilistic distribution over a vector space. We can do the same diffusion, generating, and the process and mimic any distribution on a vector space. The latent space is also a vector space. So it should just work. And because latent space is typically has a lower dimensionalities, so the training should be much more efficient, and the training for a conversion should be easier. So if everything works well, latent diffusion should reduce the computational cost for training the models. And also because it works on lower dimensional latent space. So the byproduct is that the inference and the denoise sampling steps should be also much faster. So all we need is a good encoder and a decoder. The previous research on VQ VAE and VQ GAN has paved the way for us. So in fact, both VQ VAE and VQ GAN are based on similar concept. So you see that VQ VAE is using a pixel CNN working on latent space, and the VQ GAN is using a transformer working on latent space. It's just the paper of VQ VAE is emphasis and focus on a different aspect. It is focusing on the encoder and the decoder and how we should using quantization to compress the information of a higher dimensional vector into a lower dimensional space, but it is also contains less information. So on the other hand, the VQ GAN, just like the latent diffusion, it focuses on the process on the latent space. So in the title, it actually says taming the transformer. So the focus is on the transformer part, how the transformer can be work on the latent space. Because the encoder and the decoder are pretty much the same as the VQ VAE. So the focus is shift from the encoder decoder to the process on the latent space. So we can think that the latent diffusion as a spiritual successor to VQ GAN. In fact, the encoder-decoder architecture are pretty much the same as VQ GAN. I mean, the encoder-decoder of the latent diffusion is pretty much the same as VQ GAN. Just one key difference is that the latent diffusion does not use the quantization component. It doesn't require to do so. Instead, it leverages the diffusion process and manipulate the image within the latent space on the continuous latent space. So the architecture of latent diffusion blending the ideas of previous architecture and allows us to solve an issue of the models like diffusion models that is facing. So let's look at the illustration and we can explain a little bit about the details about the actual implementation of the latent diffusion models. So you can see on the above here, we have in the pink area is represent the pixel space. So at the beginning we have an X, and which is an image, and we have an encoder, and then we get into a latent space. Z, we get a latent Z. The Z is having a lower resolution than X. So here, suppose our X has a resolution of 512 by 512, and usually we have considered as RGB has 3 channels, 3 color channels. Then this Z will have a dimension of 64 by 64, and it will have 4 channels. So we reduce our vectors dimensionalities from 512 by 512, I mean 512 times 512 times 3 to 64 times 64 times 4. Then we work on here. So you can feel that the latent used by the latent diffusion and also by the stable diffusion is kind of like a resized image with a strange channels of colors. It has 4 channels. It's not directly corresponded to the RGB channel, but encoded an area of colors into a vector. But the size is 64 by 64. It's 8 times lower. 8 times lower in width and both in width and in height. Okay, so then we do the diffusion process and on it. But when we do the training, it do the diffusion process, which means we add the noise into the latent. So we add the noise on the latent vector z. We use the same method to add the latent. That is, we add a Gaussian noise, identical Gaussian noise to each component of the vector independently. And for the denoising process, we use a unit. In fact, we are using a unit with attention block. So you can see the paper called the unit with attention block and see the detail of this architecture. So basically, the denoising process is just like other denoising diffusion models. Then when we wish to generate an image, we're using a denoising process and getting a denoised latent. Then we use a decoder to decode this 64 by 64 by 4 latent vector into pixel space and get an image of 512 by 512 with 3 color channels. The encoder and the decoder are trained separately. And also, if we wish to add some conditions, like the text prompt, it can be concatenated into the denoising process. Next, we are going to discuss how we can actually add the condition, including the prompt, into the denoising process. So let's first talk about the classifier guidance method. This is a method to use condition to guide the sampling process of our denoising diffusion model. The method is in fact proposed in the paper Diffusion Models Bitscan. So one of the milestone paper of the diffusion models. In the paper, it first formulates the conditional sampling process into a conditional probability formula. P xt condition on xt plus 1 and y. Y is the condition. In the unconditional sampling, we only need to derive xt from xt plus 1. We only need to denoise xt from xt plus 1. Recall that in the diffusion process, we add the noise into xt and increase the time step to t plus 1. So the larger the time step, the noisier the x is. So in the denoising process, we denoise from a noisy sample into the noisy x into a less noise xt. In the conditional setting, the denoising process has to be conditioned also on the condition y. This y can be a prompt or a class of the image, or maybe a reference image. So for the sake of simplicity, suppose this one is a class. Let's first think this one is a class. The probability, the conditional probability depends on both of the condition. However, for the denoise model will only has the probability of xt condition on xt plus 1 itself. So it is impossible to derive this probability from the diffusion model itself. However, under certain assumption, some reasonable assumption, and we can derive the formula and to become the product of these two probability. So the first one is the original unconditional denoising process. So we have a conditional probability of xt on the condition of xt plus 1. And the other one is the condition of y, condition probability of y condition on xt. So this one is in fact the probability given by a classifier. That is, what is, so suppose we are considering y is the class. So this one is basically saying, okay, let's take a image xt. What is the class of the content in this noise image? So for example, if our images are from the dataset MNIST, which is handwritten digits, then this y, this probability is the output of the softmax output that we get, corresponding to the probability of which digit represented in the image. So y can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we can. This is the conditional probability. Given the image, then we want to know how likely the number is written in this noise image is 0 or 1 or 2 or 3 or 4. So if this one is in another image dataset like C410 or in ImageNet, then the class might be a dog, a car, or something else. Then we can get the conditional image. So this one is basically the output of the classifier. Okay, so essentially the conditional probability that we want can be considered as a product that from the output of the denoising diffusion model and the output of the classifier. So can we use this formula into our sampling process to get a conditional sampling? So that's the idea behind the classifier guidance method. So you can see the algorithm here. We don't need to retrain anything. Suppose we already have the classifier and the diffusion model we already have, then we can do the classifier guidance method. So here our sampling is modified from the original denoising diffusion model. We can see that here, as the usual, like the usual unconditional denoising process, we got our mu and sigma. So if it is unconditional, we simply sample the xt minus 1 from the normal distribution with a corresponding mu and sigma. And also because we are considering about the log of the density function, log of the probability density function. So the product here becomes, when we take a log on it, it will become the summation of the log probability. So that's why we have a summation right here. And we plus the log of it. And we actually consider the gradient of the log. So we are consider the gradient. You can see that we are consider the gradient of a log P here. So this is the whole algorithm for sampling, denoising sampling. The good thing about it is that it doesn't require we to retrain our diffusion model, and it only requires an additional classifier. The bad news is that this classifier cannot be any classifier because we are working on noisy images. So this classifier has to be trained on noisy images. So you cannot just pull out your classifier that trained like last semester. You cannot just simply download the ImageNet classifier and work on the diffusion model. You have to train a classifier that can work on noisy images. Secondly, although here the denoising model doesn't consider the condition Y at all, but in practice, we are usually training the diffusion model with the condition. The classifier guidance method can be easily generalized to use for text prompt. Only that we need models like a clip, so it can work with an image and text together. And we have to train this clip model on noisy images. If I recall it correctly, the original latent diffusion model used the classifier guidance method. However, currently like the Stable Diffusion and other model use another method called the classifier-free guidance. Now let's talk about the classifier-free guidance method. This method is proposed in a paper dedicated to this method alone. I put the link right here, so you can check the detail from the link. It shares a similar concept to the classifier guidance method. Obviously, by the name suggests, this method does not require and rely on a classifier. But they do share a lot of common in the approach and ideas. Both of them are having a goal to return the diffusion model's ability to generate high-quality images and adding an extra element to control the image generation process through conditions like text prompts. And this extra element is something that can provide the information of the conditional probability and use this information to adjust the sampling process of the unconditional model. At least this is what the ideas begins. But in the implementations, the classifier-free guidance in fact implement the conditional probability and the unconditional probability together into just one single model in a rather elegant way. The training algorithm of classifier-free guidance is very similar to the unconditional one, except for a few modifications. The first most apparent difference is that our training samples contains not only the image but also the condition. Suppose we are thinking about the text prompt condition. Then in our training data, we should contain not only image samples, we should contain the image and the text pair as sample. So we have an image X right here and a conditional text C right here in our training data set. Then also our model should take consider of the condition. So we should modify our models accordingly to take the condition C as the input. So if we without the step number 3, then this one is a pretty straightforward extension to the original training process with a conditional input. However, in the classifier-free guidance, it has one more modification. This modification is that we wish to train an unconditional model together with a conditional model. So we wish to train them simultaneously. We don't want to train them separately. In the principle, we can do the two independent training process. One is for the conditional training, and the other one is for the unconditional training. We can do that, and later we'll see the sampling process. We can use this condition and unconditioned probability estimation into our sampling process. However, in the standard and official implementation of the classify-free guidance, it uses an elegant way to use just one single model that can both provide both the unconditional probability information and the conditional probability information. The key idea is simple. That is, we can consider an empty condition as a special case of a condition. So if the condition is simply an empty string or empty, maybe if you are doing for a class, then maybe you can define a class called the empty class. Since we are mostly thinking about the text condition, then the most natural way to consider an empty condition is an empty string, empty text. So if we treat an empty text string as an empty condition, which means no condition, then naturally, when we put this C as an empty condition into the model, then this can be viewed as an unconditional model. In the training, we simply do the conditional and the unconditional training randomly. So for some case, we keep the condition and do the conditional training, or do the training with conditional input. And for some probability, we discard the condition totally and set the condition to be an empty condition. Then in this situation, we are training an unconditional unconditional sampling model. So that is the training procedure. For the sampling process, we use the conditional model and the unconditional model to predict the noise respectively, and use the generated linear combination of this noise to be our final noise. This formula is inspired by some conditional probability formulas, but you can change the parameter W right here. This should be this should be W, not omega, because this one is W. If you are using a stable diffusion using the Comfy UI or using the A1111 Web UI, you probably have noticed there is a configurable parameter called the CFG. It doesn't stand for config, it stands for classify-free guidance. So that is a parameter you can change to have some, it will have some impact on the image generated by the model. So that CFG, because it is a classify-free guidance, so it is corresponded to the weight, the W right here. So you can choose different W to have a different generated result. Okay, so that's the classify-free guidance method. There's one obvious question about this method is that since we have already trained an conditional model. So why not just simply rely on the conditional part alone? In principle, we could do that, but there are a few reasons not to do so. First, generating a very high quality image is very difficult. It's a very difficult procedure and difficult process to find a reliable way to generate image, to train a model that can generate image with high quality. So we don't want to change it too much. That is, it is more desirable to maintain the original successful process so that we can preserve the quality. Another reason is that this approach also separates the image quality part with the text conditional part. Because the text content or the content in the image, because we wish content in the image is aligned with the content in the text. That means the content. The content and the quality can be considered as two separate concepts, and these two concepts are more or less or conceptually orthogonal. So they are totally independent to each other. So it is more ideal that we can design a training procedure that we can separate these two ideas. So by using the current algorithm, it has the kind of idea to separate the quality part into the unconditional part of the model and the content part to the conditional part. So it is kind of difficult to, it is a design choice and it may not be easily feasible. But one thing that this model obviously can do is it can generate unconditional image together with conditional image. So at least it has the ability to generate images either conditionally or unconditionally. So that is one of the obvious benefits. However, our ultimate goal is to generate images with high qualities, image with high fidelities, image with high varieties. So none of the above reasons matter if it cannot deliver the result. The fact is, this method works pretty good. It can generate good quality images. Probably due to the reasons that we discussed above. Even if that is not the case, you can always set your W to 0 so you can generate the image with the conditional part alone. Let's do a quick summarization on the architecture of Stable Diffusion. It contains three major parts. The first part is the variational autoencoder. It can convert the image from pixel space into a latent and can convert a latent back into the pixel space. It is basically very similar to the autoencoder in the VQ GAN. And the second part is the unit, which is doing the denoising job in latent space. It is using a attention unit architecture. And finally, it has a text encoder that can encode the text into some conditional encoding. And we use the classifier-free guidance, with the classifier-free guidance method to use this condition to guide the image generation. Although latent diffusion model is designed to solve the issue of efficiency so that it can be trained more efficient than a diffusion model that is trained on pixel space, it is still very expensive. You still need billions and billions of image and text pair of data. and it requires a lot of GPU. It has been estimated at the range of like $30,000 to train a model that has comparable quality of the Stable Diffusion 1.5 or 1.4. It is not something that everybody can do in their home computer or lab computer. It requires a cluster to do so. So since this model has been available so that everyone can download it and deploy it in your machine, and we are unable to, or not easy to train it from scratch. So one way to use this model is to just piggyback on this model and to do something that we can customize it to do. So for example, one thing that we wish to do is to make the Stable Diffusion model to generate some new items. Perhaps it is a character in a fiction, like in a TV, in an anime, in a movie. But during the time period of training the Stable Diffusion, that character or that object has not been invented or designed yet. But we wish to add this new character to the model so that the Stable Diffusion can recognize this new character or new object. Or maybe we wish the Stable Diffusion to recognize a new style of image, like a painting of some artist or some style of some the movie style of some director, maybe. So how do we do that? Most straightforward way or simple naive way is to do the texture inversion. It was quite popular at the early stage of the Stable Diffusion. Currently, because there are more advanced methods, so it kind of, the popularity of the texture inversion is kind of fade, but it is still a very useful tools that you can employ it with other method, because it is some kind of basic tools that you can use it combined with other technique, and not only with the Stable Diffusion only. This technique is very general, so you can work with other model as well. Maybe not even the text model, maybe not the image generation model, maybe with a language model, maybe with a video generation model or audio generation model. So the idea is still worth knowing. So let's see what the task it can do. So let me turn on the laser point. So you can see the thing that we want to do is to ask the diffusion model to recognize a new type of object. And this object doesn't yet have a name. So we want to add a new vocabulary into the text encoder and hope that the diffusion model can recognize this new vocabulary. So for example, in this case, we give a few example image here. You can see that it is some colorful teapot with certain shape. So we hope we can give it a new name, called it S star. It's just a new symbol, and we wish the Stable Diffusion to recognize this S star symbol to be this type of object. So after our processing of the texture inversion algorithm, the desired result is that when we give a prompt like this, the manga drawing of a steaming S star, it will have a manga drawing of it with steaming, and S star watering can. So instead of producing a teapot, it produces a watering can. But you can see the similarity between the samples and these generated images, and like S star, Death Star, and a poster of the movie, the teapot starring S star. You can get the idea. So the idea is that we add this new vocabulary into the Stable Diffusion system. So first of all, we have to add one more vocabulary into the text encoder. The text encoder is kind of like the transformer architecture that we have introduced in previous lecture. So it contains a tokenizer and a text encoder to encode into a latent. Encode the whole string into a latent. So the first thing, we need to add this new symbol S star to the vocabulary list, because we know that like we do like in a BPE or like other ways to do the tokenizer, each vocabulary has an index. So the first one is simple. We add a new index. Perhaps suppose we already have like 5,000 vocabulary in our vocabulary set. So we add a new one and we label it as 5,000 plus 1. Well, that's easy. The difficult part is that for each token, for each index, we're going to have an embedding lookup table. This embedding lookup table was trained during the training of that text encoder. So maybe using a BERT way or using a GPT way or using other ways to do that. But it has already been trained. Our newly added vocabulary doesn't have an entry in this embedding lookup table. So we initialize with a random one, and then we are going to train it in a procedure so that it can find an adequate value of the embedding in this lookup table. So suppose we already have the embedding, then it runs in the text transformer as usual, and we can get a conditional latent, conditional encoding for the text, and concate this one into the input in the diffusion model for sampling or denoising. So the idea is straightforward. We run the diffusion process and we fix almost everything. We fix the transformer, text transformer. We fix the denoising sampler. We fix everything except the entry of the embedding of the S star. We only train the embedding of S star. So we do the same thing, like right here. And we do the backpropagation to find the gradient of this one. We have because we have these samples, right? In the previous slide, we have a sample of this Calaver teapot. So we simply use this limited sample and run the denoising process. And then we hope we add various different noises and try to denoise back to the original one. In fact, in the training, we only need to predict the noise from the noisy image and compute the mean square error. So we can compute those errors. And because everything is fixed, the only trainable thing in this procedure is the entry in the lookup table for S star. So that is the embedding of S star. So we try to adjust the embedding of S star so that the recovery process can be as accurate as possible. In the end, we will find a suitable embedding for S star. So this one, the suitable means, or adequate embedding means that because everything is fixed, so we already has a rule to use the encoder, to use the text encoding, to use the embeddings. So it will find a suitable value so that the encoder will treat it as the semantic of the sample image, the object, the semantic of this object in the sample images. To be more precise, for all these images, we do some simple augmentations so that we can have more samples. And we also construct some text related to this one, like a picture of S star or an object S star in this painting, or a picture, photograph of S star, something like this one. We'll have a template. So each image are pairing with several text sentences. And each one are containing the S star, describing this object as S star. So although we only have very limited samples, we still have a healthy training data set, a healthy number of training data, because we have some augmentation. Each image has some number of different sentences corresponding to this image. And plus, we can use different level of noises in the step. Although we have very limited data, like 2 or 3, or maybe like a very little data, maybe if we have some more data, like 10 or 20, but sometimes we only have like 2 or 3. But in any case, we can do the training. And there are only very limited parameters need to be trained. That is the embedding of S star. So this, you can imagine this procedure works and we can find the corresponding object. Although this corresponding embedding for the object. So this method actually works. It just doesn't work that well. So for example, if you are trying to training a face of a celebrity, there are some chance it kind of looks similar or have some features of that celebrity, but you may recognize the generated person as a different one and not the same person. So your miles may vary. Depends on the data you are given, and sometimes are more successful than the other. And of course, sometimes they are not as successful as other times. So not only it can be used to add some new object, it can be used to add some new vocabulary for the style. For example, this is the one. I have to say first that this one is a very early work, so it is not quite good. It can be done better than this one, but you might imagine some typical result that you can get for texture inversion. So in this case, I was trying to do the texture inversion on the style of the anime JoJo. So it should supposed to be the JoJo style. That was a very early attempt, so I have made some mistakes like the aspect ratio. So you can see that although the JoJo is kind of famous for its unnatural posing, so it may not be that strange for like strange aspect ratio, but the fact here is that I have made a mistake that I didn't adjust the aspect ratio right for the training. But still, you can see that it captures some characteristic of the JoJo animation. Okay, so that is one way that we can customize our model to do something more than the off-the-shelf Stable Diffusion can do. Another way to customize a model is a method called the Dream Boost. The Dream Boost can be considered as a spatial type of the fine-tuning. It is originally developed by Google team, and originally it is applied on Imagine. That is a text-to-image diffusion model developed by Google. But very soon it has been adopted and used on Stable Diffusion as well. The functionality is similar to texture inversion, but it involved with the actually fine-tuning. So we still need a few examples of a spatial object or style. In this example, we are considering a specific type of dog. So we call it a feed dog. A feed is a type prefix of the this type. So it is used in combination with the word dog. So when we say feed dog, we mean this type of dog. So this new identifier can be, we can use a new vocabulary just like texture inversion. So we do some similar things like texture inversion, or it can be simply used in existed vocabulary and we do some specific combination as this unique identifier. So let's just consider the second case that we are using some combination of existing tokens without introducing new vocabulary. So after the Dream Boost procedure, so we have a few examples of this object and the original text-to-image model. In the paper, it is applied to the Imagine, and we can adapt it to Stable Diffusion as well. Then after this procedure, we are getting a customized, or maybe we should say the fine-tuned model. In the paper, it used the word personalized text-to-image model, but it's just a fine-tuned model. So in this fine-tuned model, if our prompt contains this specified unique identifier, then it will generate the content as desired. So like there's a feed dog in the beach, and we can see this type of dog in an image with a background of a beach, and a feed dog walking on a colorful carpet, and we can definitely see the feed dog right here, and it is on a colorful, rainbow-like color carpet. So it works similar to, its functionality is similar to the objective. Our goal is similar to the texture inversion, only that it usually produces much better result. So this is how it works. Basically, it is just fine-tuning the whole thing. In Imagine, because Imagine has Imagine works like this way. It first generates a small low resolution image, like 64 by 64. Then it uses a super resolution module to super resolution the 64 by 64 into a high resolution image. Like we said, one of the major issues of the diffusion model is it does not easy, or it costs a lot to train a model that can generate a high quality image with high resolution. So there are many ways to get around with it. One way is the latent diffusion. We have covered it earlier. And you can imagine another way is we first generate a low resolution image by using a diffusion model. Then we try to super resolution it into a higher resolution image. So imagine is along this approach. So it basically has two parts. So for the first part, the diffusion part, it basically is just fine-tuning the unit, the denoising part. So the text encoder is fixed unless you want to also use the texture inversion along with the Dream Boost. Otherwise, we fix the text encoder. So the typical usage is using the existing vocabulary, existing tokens to combine a new identifier. We don't need to introduce a new vocabulary. Okay, so basically we're just fine-tuning the denoising unit. And because it has a super resolution component, we also need to fine-tuning the super resolution part if we are applying it to Imagine. But since the Stable Diffusion doesn't have a super resolution part, so this one is totally discarded. So when applying to the Stable Diffusion, we only fine-tune the unit part. So you may think, okay, why does this one even need a name? Because it is just fine-tuning. If you think so, you are not alone, because I also think so. The Dream Boost is pretty much referred to the fine-tuning of the unit, although it has another spatial property right here. There's a very unique or spatial treatment of the fine-tuning. That is, in the training of the Dream Boost, not only you need to train the feed dog examples, the example image from the feed dog, you also need to train the general dog. So in this case, the class of dog will not collapse. So the argument is that if you don't do these things, the model will very likely to collapse the mode of dog, because it can simply discard the feed keyword here, because dog is a very strong word. So the model can simply learn that, okay, maybe you want me to generate dog only in this style. So it is very possible that whenever the model sees the personalized or fine-tuned or customized model, when the model is customized, when it sees the prompt dog, it will only generate this dog. Nothing can prevent this happen if you only train on the feed dog samples. However, to prevent this happen, the Dream Boost suggests that not only we should train on the feed dog example, we should also train on the general dog samples. So this is something unique, or this is a feature that a characteristic that in the training of Dream Boost. However, this type of training is not uncommon. When we try to customize the model to prevent it overfitting too quickly, when we try to fine-tune a model with a very limited data to prevent the model to be overfitting too quickly, it is very common to combine with more data from the original training dataset with the limited data. So it won't be converged to the very limited data too fast, too quickly. Okay, so basically this is just a Dream Boost, and this is a very common technique to customize the model. Another popular way to customize Stable Diffusion model is using LoRa. LoRa stands for Low Rank Adaptation. Originally, it is designed to fine-tune large range models, but it can apply to pretty much all kind of neural network models, including Stable Diffusion. And it is getting very popular in the customization of Stable Diffusion models. You can find a lot of different LoRa models for the Stable Diffusion models. Like texture inversion and the Dream Boost, it can be used to customize the model to generate new concept, new object, new styles. The difference is that we usually expect, when training LoRa, we usually expect to have more samples than Dream Boost or texture inversions. Like the Dream Boost, it is a method for fine-tuning, but it is focusing on a different issue or part of fine-tuning. The Dream Boost is focusing on prevent the mode collapse for the general class and the spatial class, or like the dog vs dog example. But for LoRa, the goal of LoRa is try to find a way to do the fine-tuning more efficiently in the sense of the parameter counts. So the goal is to use a small number of parameters to fine-tuning the models. So on the slide, you can see that it is fine-tuning the Stable Diffusion model into different styles. So when it generates the same character, you can see that it can, with the same prompt, it can generate the images in different style. With the relation between LoRa and the base model is we add some variation into the original model. And in fact, from the mathematical formulas, you can see that the variation part of the LoRa. We have a lot of linear mappings in our neural network models. For MLP, most layers are linear part followed by some nonlinear activation function. For the transformer or attention block, we also have a lot of linear mapping. Also recall that we first project each of the features into key, query, and the value. We also do another round of MLP at the end as a final step of the attention block. So we do have a lot of linear mapping. We do have a lot of linear mapping in the attention block. And all these attention block, all these linear mapping are very high dimensional. Typically, it is something like 2000 by 2000 matrix. So we store the linear transformation in something like 2000 by 2000 matrix. This is a huge matrix because it contains like 4 million parameters. If we want to do a full fine-tuning, we're going to adjust all of these 4 million parameters in this one single linear mapping alone. And one unit or one large language model contains a lot of attention block, and each attention block contains several of this size of the matrix. If we can adjust only a few parameters, that will be ideal. But which parameters should we choose? This is a question. This is a problem because the original model is pretty good, either a large range model or like the diffusion model, like a Stable Diffusion. All of this model has already trained on billions of data, so they are pretty good as a base model. We only want to change it a little bit, so the difference of the customized model and the original model should be very small. So if we write it in this way, W0 is the original weight of the linear mapping, which is one layer in the whole model. And the customized or fine-tuned model, in the fine-tuned model, the matrix becomes W0 plus delta W. And delta W should be very small, should be a very small one. There are many ways to measure the smallness of a matrix. One way to measure it is the rank. This is one of the popular way to measure the size or measure the how small or how big a matrix is. So if a matrix has a very low rank, we are consider it as a small one. And when it contains a full rank, we consider it as a big one. There are many usage of the rank in a different field of computer science. So in this case, we are assuming the small difference, the delta W, to be a low rank matrix. But how do we parameter a low rank matrix? So one way to do that is to decompose the matrix into a matrix multiplication of two matrices. So each of the matrices has a low rank. So the combination of both of them is going to be low rank. Suppose the original mapping is from dimension 2000 to a dimensional 2000 dimensional space. So the pre-trained weight contains 2000 times 2000 parameters, which is 4 million parameters. So we can choose a small rank like 100. And A will be a matrix of 2000 by 100. Also say our R is 100. So this A is from 2000 to 100. So it is a linear mapping from a 2000 dimensional space into a 100 dimensional space. In the matrix form, it is going to be a matrix of 2000 by 100. Depends on you want to the direction you are doing the matrix multiplication. But it only contains 2000 times 100 parameters, which is 200,000 parameters. It is similar for the matrix B. It is a linear mapping from dimension 100, a space of dimensional 100 to a space, back to a space of 100, back to a space with dimension 2000, back to a space of 2000 dimension. It also requires 200,000 parameters. So in total, it requires 400,000 parameters, which is still kind of large, but compared to 4 million, it is very small. Like an autoencoder. An autoencoder usually has a bottleneck. So this R is like a bottleneck. We are compressing the 2000 dimensional space into a 100 dimensional space and make it back to the 2000 dimensional space. Except it is not an autoencoder. It just has a similar format like a PCA or autoencoder, but it has a totally different objective. But they share a common property, that is, we are trying to compress the things into the important ones. So we are only using very little parameters compared to the original 4 billion parameters to do our fine-tuning. So we are fixing the pre-trained weight and fine-tuning only on this part. And our final fine-tuned weight is W0 plus delta W. And this delta W is represent a matrix multiplication BA. It is not entirely clear this method should work. We know that it requires only a few very small number of parameters. But does this fine-tuning actually work? So this requires some experiment and to see a result. It turns out it works pretty well on large range model and also on Stable Diffusion. There are many other different ways to do fine-tuning with very limited parameters. This kind of fine-tuning called the parameter efficient fine-tuning. So in fact, this is not the only way to do the PEFT or parameter efficient fine-tuning, but this one is a common way, and it works pretty well on various applications. For the last part of this lecture, we're going to talk about control net. Control net is one of a way to extend the capability of Stable Diffusion or other model to accept a new image condition. So for example, the original Stable Diffusion only accepts text prompt as a condition, but with the help of control net, it can accept an image, in this case, a pose, a human pose, as the conditional input in addition to the original text prompt condition. And we can ask the Stable Diffusion to generate image of people aligned with this pose. You can still use the text prompt as your condition. So in this one, it maybe says it is a chef cooking the meals. So the generated image will become a chef and has the pose corresponding to this conditional input. Another way to use the conditional input is we can have a semantic segmentation of an image and then use this semantic segmentation and generate new images aligned with this segmentation. And as it before, you can still use the text prompt as a condition along with this image segmentation. Another interesting way to use it is to use a depth map as a conditional input. So we can generate images aligned with this depth map. The good thing is there are many models exist that can generate depth map from single image. So combine those models, we can easily use an image as a reference of structure and generate different content according to this structure. So how does control net work? Consider we have some neural network block. Although this description is more abstract and generic, let's simply consider our neural network block accepting the input of it is X, which is a 2D input, like an image or a hidden layer in a convolutional neural network. And the output is Y. So in order to have a new conditional input to this block, we do the following modification. First of all, we copy the original weight from this neural network block into a trainable copy. Then consider our condition is also a 2D input, two-dimensional input with some channel, just like an image or hidden states or in a convolutional 2D network. So first of all, we do a zero convolution and we do the addition, summation of the original X with this result of the zero convolution of the original condition. So the zero convolution is simply a convolution, but its kernel is all zero. Kernel and the bias is all zero. So the output, at least at the very beginning, it should be all zero. So we plus the output of this zero convolution with X and feed it into the trainable copy. And we do the zero convolution on the output of the trainable copy again and add back it into the output of the original network block and get our modified output. So as you can see in the architecture, if you fill this as a whole, then it is a neural network block which accepts two inputs. One is X and one is Z. And it outputs something comparable to the original output. At least they have the same dimension, have the same shape and dimension. So this one at least achieve one of our goals, because we wish to add the new conditional input into our original neural network block. Another thing that we need to note is that we don't want to change the original model too much. Our original model is Stable Diffusion model, which is trained using a lot of GPU hours with a lot of data, and it has an ability to generate high quality images aligned with the text prompt. It's not something that we can improve easily, so we don't want to destroy it, we want to keep it. So we only want to adjust the model's weight just a little bit to satisfy our need. We don't want to change it too much, just like the case in LoRa. So in the design of a control net at the very beginning of the training, the C is passed through a zero convolution, so it makes no change to the X, and the output is also passed through a zero convolution. So it adds nothing to the output of the original neural network block. So it's going to have the the same input and output as the original Stable Diffusion. So after training a while, it will change. The zero convolution will be changed. If we set the learning rate correctly, so this change will not be too much. It will be start from the zero, so it will, at least at the beginning, it will around the zero. So it can be considered as a small adjustment to the original neural network block. So in this way, we can add a new conditional input C into the Stable Diffusion model. So how do we apply this modification to the actual Stable Diffusion model? We are doing so for the UNet part. So this one is the UNet part, the component, the layers of the UNet part. We are applying the control net modification to the up block. Also in a unit, we have down blocks and up blocks. We are applying this modification to the up blocks. So these are basically just copies of these blocks, like this one, the A by A block and 16 by 16 block. So we are just copying this block right here. In fact, we're just doing the control net modification and apply this to the up blocks. So that's it. That's pretty much how the control net works on the Stable Diffusion. And no matter your input condition is pulsing, semantic discrimination, or a depth map, or some other image condition, all we need to do is do a training. That being said, the training is not easy. It still requires a lot of time to do a training. The repo of the control net provides a small example, toy example, allow you to practice the training. But the training is not easy. It takes a while, and even if you are doing it right, it takes a long time to converge, and you need to prepare a suitable dataset. The dataset is more or less like the dataset of the pixel-to-pixel application. So like what we did in our homework, because pixel-to-pixel is popular and still being very popular and a useful model. So there are many different ideas can be applied and used for control net. But you probably need more data than you training the pixel-to-pixel models. And it is much difficult to train the control net than to train a pixel-to-pixel model. So you don't see that many different control net models available. But the idea and the design of the control net is very interesting. So maybe you can use this idea on other projects. Okay, so that's the materials we are going to cover today.